We live our lives without truly understanding the workings of the universe. We do not ponder the mechanisms that produce the sunlight essential for our existence. We do not think about gravity, which keeps us anchored to the earth, preventing it from casting us into space. We are uninterested in the atoms that make up our bodies, and upon whose stability we significantly depend. Aside from children, who are still too naive to refrain from asking such profound questions, few people grapple with why nature is the way it is. Where did the cosmos come from, and has it always existed? Could time ever reverse itself, such that an effect precedes its cause? There are even children, whom I have encountered, who want to know what a black hole looks like, what the smallest particle of matter is, and what allows us to remember the past while forgetting the future. If chaos truly existed before, how did we arrive at the visible order we see now? And why does the universe exist at all? In our society, it is common for parents and teachers to shrug their shoulders or resort to vaguely remembered references to religious legends in response to these questions. Some dislike such topics because they highlight the limitations of human understanding. Yet, the advancement of philosophy and the natural sciences has largely progressed due to such inquiries. More and more adults are showing interest in these questions, and the answers can sometimes be completely unexpected. Differing in scale from both atoms and stars, we are expanding the horizons of research to encompass both very small and very large objects. What do we know about the universe, and how did we come to know it? Where did the universe come from, and what will happen to it? Did the universe have a beginning? And if it did, what occurred before that beginning? What is the essence of time? Will it ever come to an end? The achievements of physics in recent years, which we owe in part to fantastical new technologies, finally allow us to obtain answers to at least some of these long-posed questions. In time, these answers may become as obvious as the fact that the Earth revolves around the Sun, or perhaps as absurd as the towers of turtles. Only time, whatever it may be, will determine that. As early as 340 years before our era, the Greek philosopher Aristotle presented two compelling arguments in favor of the idea that the Earth is not a flat disk, but a round sphere. First, he deduced that a lunar eclipse occurs when the Earth is positioned between the Moon and the Sun. The Earth always casts a round shadow on the Moon, which can only happen if the Earth is spherical. If the Earth were a flat disk, the shadow would take the shape of an elongated ellipse, unless the eclipse always occurred precisely when the Sun was aligned with the axis of the disk. Second, from his travels, the Greeks knew that in southern regions, the North Star appears lower in the sky than in northern regions. Since the North Star is positioned above the North Pole, it would be directly overhead for an observer standing at the North Pole, while someone at the equator would see it on the horizon. By knowing the difference in the apparent position of the North Star in Egypt and Greece, Aristotle was even able to calculate that the length of the equator is approximately 400,000 stadia. The exact length of a stadia is unknown, but it is close to 200 meters, meaning Aristotle's estimate is about twice the current measurement. The Greeks had a third argument for the spherical shape of the Earth. If the Earth were not round, why do we first see the sails of a ship rising above the horizon before we see the ship itself? Aristotle believed that the Earth was stationary, with the Sun, Moon, planets, and stars revolving around it in circular orbits. He thought this because, in accordance with his mystical beliefs, he considered the Earth to be the center of the universe and circular motion to be the most perfect. In the 2nd century, Ptolemy expanded upon Aristotle's ideas into a complete cosmological model. The Earth stands at the center, surrounded by 8 spheres carrying the Moon, Sun, and 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves were thought to move in smaller circles attached to their respective spheres. This explained the rather complicated paths that the planets appear to take. The last sphere contained the fixed stars, which, remaining in the same positions relative to one another, moved across the sky as a single entity. What lay beyond the last sphere was not explained. In any case, it was no longer part of the forces that humanity could observe. Ptolemy's model allowed for reasonably accurate predictions of the positions of celestial bodies in the sky. But for precise predictions, he had to accept that the Moon's trajectory in some places came twice as close to the Earth as in others. This meant that at one position, the Moon would appear twice as large as at another. Ptolemy was aware of this flaw, yet his theory was accepted, albeit not universally. The Christian Church accepted Ptolemy's model of the universe as not contradicting the Bible, as it left ample room beyond the sphere of fixed stars for hell and paradise. However, in 1514, the Polish priest Nicholas Copernicus proposed an even simpler model. Initially, fearing that the Church would label him a heretic, Copernicus promoted his model anonymously. His idea was that the Sun is stationary at the center, with the Earth and other planets revolving around it in circular orbits. It took nearly a century for Copernicus's idea to be taken seriously. 2 astronomers, German Johannes Kepler and Italian Galileo Galilei, publicly supported Copernicus's theory, despite the fact that the orbits predicted by Copernicus did not completely match the observed ones. The theories of Aristotle and Ptolemy came to an end in 1609 when Galileo began observing the night sky with the newly invented telescope. Aiming the telescope at the planet Jupiter, Galileo discovered several small moons orbiting Jupiter. This indicated that not all celestial bodies necessarily revolve directly around the Earth, as Aristotle and Ptolemy had believed. Of course, one could still maintain that the Earth remained at the center of the universe, and that Jupiter's moons followed a very complicated path around the Earth, making it seem as though they were orbiting Jupiter. However, Copernicus's theory was significantly simpler. As for Johannes Kepler, he modified Copernicus's theory based on the assumption that planets move in ellipses, stretched circles, rather than perfect circles. Finally, the predictions matched the observational results. Kepler's elliptical orbits were an artificial ad hoc hypothesis and not particularly elegant, as an ellipse is a far less perfect shape than a circle. He discovered, almost by chance, that elliptical orbits aligned well with observations. Kepler never managed to connect this fact with his idea that planets revolve around the Sun due to magnetic forces. The explanation only came much later, in 1687, when Isaac Newton published his book, Mathematical Principles of Natural Philosophy. In it, Newton not only proposed a theory of the motion of material bodies through time and space, but also developed complex mathematical methods necessary for analyzing the motion of celestial bodies. Furthermore, Newton postulated the law of universal gravitation, stating that every body in the universe attracts any other body with a force that is greater the larger the masses of the bodies and the smaller the distance between them. This is the very force that causes objects to fall to the earth. The story that Newton was inspired by an apple falling on his head is almost certainly a myth. Newton himself only stated that the thought of gravity came to him while he was in a contemplative mood, prompted by the falling apple. Newton then showed that, according to his law, the moon moves in an elliptical orbit around the Earth under the influence of gravitational forces, while the Earth and planets revolve in elliptical orbits around the Sun. Copernicus's model helped eliminate Ptolemy's celestial spheres, as well as the notion that the universe has some natural boundary, since the fixed stars do not change their positions in the sky, except for their circular motion associated with the Earth's rotation. Naturally, it was reasonable to assume that the fixed stars are objects similar to our Sun, only much more distant. Newton understood that according to his theory of gravitation, stars must attract one another, and thus they seemingly cannot remain completely motionless. Shouldn't they fall into one another if they came close enough? In 1691, in a letter to Richard Bentley, another prominent thinker of the time, Newton stated that this would indeed happen if we had only a finite number of stars in a finite region of space. However, since there are stars beyond the considered region, according to Newton's law, additional stars would not affect the original ones on average. That is, stars would fall toward the center of the designated area at the same rate, regardless of how many stars we added. They would always tend toward the center. Nowadays, it is known that an infinite static model of the universe is impossible if gravitational forces remain attractive. It is interesting to consider the state of scientific thought before the 20th century. No one even considered the idea that the universe might expand or contract. Everyone believed that the universe either always existed in an unchanging state or was created at some moment in the past. This approach can partly be explained by humanity's inclination to believe in eternal truths, as well as the particular allure of the idea that, while they themselves age and die, the universe remains eternal and unchanging. Even those scientists who understood that Newton's theory of gravitation made a static universe impossible did not entertain the hypothesis of an expanding universe. They attempted to modify the theory by making the gravitational force repulsive at very large distances. This did not significantly alter the predictions of planetary motion, but it allowed for an infinite distribution of stars to remain in equilibrium, as the attraction of nearby stars was counterbalanced by the repulsion of distant ones. However, we now consider such equilibrium to be unstable. In reality, if stars come slightly closer in some area, the gravitational forces between them will increase and become greater than the repulsive forces, causing the stars to draw even closer together. Conversely, if the distance between stars increases slightly, the repulsive forces will dominate, and the distance will continue to grow. Another objection to the model of an infinite static universe is often attributed to the German philosopher Heinrich Walter, who published a work on this model in 1823. In fact, many of Newton's contemporaries were engaged in the same task, and Walter's paper was not the first to raise serious objections. The only reason the earlier works became widely cited is that they were the first. The objection is as follows. In an infinite static universe, any line of sight must intersect with a star, but then the night sky should glow brightly, like the sun. Walther's counterargument was that the light coming to us from distant stars must diminish due to absorption by the matter in its path. However, in that case, this matter must heat up and glow brightly like the stars. The only way to avoid the conclusion of a brightly glowing night sky is to assume that the stars did not shine forever, but ignited at some specific moment in the past. Then the absorbing matter may not have had time to heat up, or the light from distant stars may not have reached us yet. This raises the question, why did the stars ignite? Of course, the problem of the universe's origin has occupied human minds for a very long time. According to several early cosmogonies and Jewish, Christian, and Muslim myths, our universe emerged at a specific and not very distant moment in the past. One basis for such beliefs was the need to find a first cause for the existence of the universe. Every event in the universe is explained by pointing to its cause, that is, another event that occurred earlier. Such an explanation for the existence of the universe itself is only possible if it had a beginning. Another basis was proposed by St. Augustine. The Orthodox Church considers Augustine to be blessed, while the Catholic Church considers him a saint. He pointed out that civilization progresses, and we remember who performed certain deeds and who invented what. Thus, humanity, and therefore the probable universe, is unlikely to exist for very long. St. Augustine accepted the date of the universe's creation, corresponding to the book of Genesis, approximately 5,000 years before Christ. Interestingly, this date is not far from the end of the last ice age, 10,000 years before Christ, which archaeologists consider the beginning of civilizations. Aristotle and most other Greek philosophers disliked the idea of the universe's creation, as it was associated with divine intervention. Therefore, they believed that humans and their surrounding world existed and would continue to exist eternally. The argument regarding the progress of civilization was considered by ancient scholars, who concluded that the world periodically experienced floods and other cataclysms that continually returned humanity to the starting point of civilization. Questions about whether the universe arose at some initial moment in time and whether it is limited in space were later closely examined by the philosopher Immanuel Kant. In his monumental and very dense work, Critique of Pure Reason, published in 1781, he referred to these questions as antinomies, or contradictions of pure reason, as he saw that neither the thesis of the necessity of the universe's beginning nor the antithesis of its eternal existence could be proved or disproved equally. Kant argued for the thesis by stating that if the universe had no beginning, then every event would be preceded by an infinite period of time, which he considered absurd. Support for the antithesis, he claimed, comes from the fact that if the universe had a beginning, it would have been preceded by an infinite period of time, raising the question of why the universe suddenly emerged at a particular moment in time. In reality, Kant's arguments are essentially the same for both the thesis and the antithesis. He operates under the silent assumption that time is infinite in the past, regardless of whether the universe has existed eternally or not. As we will see later, the concept of time is meaningless before the emergence of the universe. Blessed Augustine first pointed this out when he was asked what God was doing before creating the universe. Augustine never replied in the spirit of suggesting that God was preparing hell. For those who ask such questions, he stated that time is an inherent property of the universe created by God, and therefore there was no time before the universe came into being. When most people believed in a static and unchanging universe, the question of whether it had a beginning or not essentially belonged to the realm of metaphysics and theology. All observable phenomena could be explained both by a theory in which the universe exists eternally, and by a theory stating that the universe was created at a specific moment in time. Thus, everything could appear as if it had existed eternally. However, in 1929, Edwin Hubble made a groundbreaking discovery. It turned out that, no matter where one looked in the sky, all distant galaxies are rapidly moving away from us. In other words, the universe is expanding. This means that, in earlier times, all objects were closer to one another than they are now. This suggests that there was a time, approximately 10 or 20,000 million years ago, when they were all in one place, resulting in an infinitely high density of matter. Hubble's discovery shifted the question of how the universe originated into the realm of science. Hubble's observations indicated that there was a time known as the Big Bang, when the universe was infinitely small and infinitely dense. Under such conditions, all scientific laws lose their meaning and do not allow for predictions about the future. If any events occurred even earlier, they could not have influenced what is happening now due to the absence of observable consequences. They can simply be disregarded. The Big Bang can be considered the starting point of time in the sense that earlier times would be simply undefined. It is important to emphasize that this starting point of time is very different from anything proposed before Hubble. The beginning of time in a static universe is something that must be determined by something existing outside the universe. There is no physical necessity for the beginning of the universe. The creation of the universe by God can be imagined to have occurred at any moment in the past. However, if the universe is expanding, there may be physical reasons for it to have a beginning. One can still envision that it was indeed God who created the universe at the moment of the Big Bang, or even later. But it would be absurd to claim that the universe existed before the Big Bang occurred. The idea of an expanding universe does not exclude a creator, but imposes limitations on the possible date of his creations. To discuss the essence of the universe and whether it had a beginning and will have an end, one must have a good understanding of what a scientific theory actually is. I will adhere to the simplest viewpoint. A theory is a theoretical model of the universe or some part of it, supplemented by a set of rules connecting theoretical quantities with our observations. This model exists only in our minds and has no other reality, regardless of the meaning we attach to that word. A theory is considered good if it meets two requirements. First, it must accurately describe a wide class of observations within a model that contains only a few arbitrary elements. Second, the theory must make definite predictions regarding the results of future observations. For example, Aristotle's theory, which posited that everything is composed of four elements, earth, air, fire, and water, was simple enough to be called a theory, but it could not yield any definite predictions. Newton's theory of gravitation, on the other hand, was based on an even simpler model in which bodies attract each other with a force proportional to a certain quantity called their mass, and inversely proportional to the square of the distance between them. However, Newton's theory accurately predicts the motion of the sun, moon, and planets. Any physical theory is always provisional in the sense that it is merely a hypothesis that cannot be proven, no matter how often the agreement between the theory and experimental data is confirmed. One cannot be certain that the next experiment will not contradict the theory. At the same time, any theory can be disproven by a single observation that does not align with its predictions. As the philosopher Karl Popper pointed out, a necessary characteristic of a good theory is that it allows for predictions that can, in principle, be experimentally disproven. Each time new experiments confirm the predictions of a theory, the theory demonstrates its vitality, and our faith in it strengthens. However, if even one new observation does not align with the theory, we must either abandon it or revise it. Such is the logic, although, of course, one is always entitled to question the competence of the person conducting the observation. In practice, it often turns out that a new theory is actually an extension of a previous theory. For instance, extremely precise observations of the planet Mercury revealed slight discrepancies between its motion and the predictions of Newton's theory of gravitation. According to Einstein's general theory of relativity, Mercury should move slightly differently than predicted by Newton's theory. The fact that Einstein's predictions align with observational results, while Newton's do not, became one of the decisive confirmations of the new theory. In reality, we still use Newton's theory. As in the cases we typically encounter, its predictions differ very little from those of general relativity. Newton's theory also has the significant advantage of being much easier to work with than Einstein's theory. The ultimate goal of science is to create a unified theory that describes the entire universe. In addressing this task, most scientists divide it into two parts. The first part involves the laws that allow us to understand how the universe changes over time. Knowing what the universe looks like at a given moment, we can use these laws to predict what will happen to it at any later moment. The second part concerns the problem of the initial state of the universe. Some believe that science should only deal with the first part, considering the question of what came first to be a matter of metaphysics and religion. Proponents of this view argue that since God is omnipotent, it was within His will to initiate the universe however He wished. If they are correct, then God had the option to allow the universe to develop completely randomly. However, it seems He preferred that it evolve quite regularly according to certain laws. But then it is equally logical to assume that there are also laws governing the initial state of the universe. It turns out to be very difficult to create a theory that describes the entire universe all at once. Instead, we break the task into parts and build partial theories. Each of these describes a limited class of observations and makes predictions regarding them while neglecting the influence of all other quantities or simplifying them into simple sets of numbers. It is possible that this approach is entirely incorrect. If everything in the universe fundamentally depends on everything else, then perhaps by studying separate parts of the problem in isolation, we cannot get closer to a complete solution. Nevertheless, in the past, our progress has followed this path. A classic example is Newton's theory of gravitation, which states that the gravitational force acting between two bodies depends only on one characteristic of each body, namely its mass, and does not depend on what substances the bodies are made of. Therefore, to calculate the orbits of the Sun and planets, it is not necessary to have a theory of their structure and composition. Currently, there are two main partial theories for describing the universe: general relativity and quantum mechanics. Both are the result of immense intellectual efforts by scientists in the first half of our century. General relativity describes gravitational interactions and the large-scale structure of the universe, that is, structures ranging from several kilometers to a billion kilometers, or to the size of the observable universe. Quantum mechanics, on the other hand, deals with phenomena at extremely small scales, such as 1/millionth of 1/millionth of a centimeter. Unfortunately, these two theories are incompatible. They cannot both be correct at the same time. One of the main directions of modern physics research is the search for a new theory that would unify the two previous ones into one: quantum gravity theory. If you believe that the universe evolves not arbitrarily, but according to certain laws, then eventually you will have to unify all partial theories into a single comprehensive theory that describes everything in the universe. However, the search for such a unified theory involves one fundamental paradox. Everything mentioned above about scientific theories assumes that we are rational beings capable of making any observations in the universe and drawing logical conclusions based on those observations. In such a framework, it is natural to assume that we could, in principle, get closer to understanding the laws governing our universe. But if a unified theory truly exists, it must also somehow influence our actions. And then the theory itself must determine the outcome of our search. This raises the question: why should it predetermine that we draw the correct conclusions from our observations? Why not just as easily lead us to incorrect conclusions or to none at all? I can offer only one answer to these questions. It is based on the Darwinian principle of natural selection. My idea is that in any population of self-replicating organisms, genetic variations and differences in the upbringing of individual organisms are inevitable. This means that some individuals are better than others at drawing correct conclusions about the world around them and acting according to those conclusions. Such individuals will have a greater chance of survival and reproduction, making their way of thinking and behavior dominant. In the past, intelligence and the ability to make scientific discoveries undoubtedly provided a survival advantage. However, it is not at all obvious that this is still true today. Our scientific discoveries may even lead to our destruction. But even if that does not happen, a complete unified theory is unlikely to significantly affect our chances of survival. Nevertheless, since the universe evolves in a regular manner, it can be assumed that the reasoning abilities we have acquired through natural selection will manifest in the search for a unified theory and help avoid incorrect conclusions. Since the existing partial theories are quite sufficient to make accurate predictions in all situations except the most extreme, the search for a final theory of the universe does not meet the requirements of practical feasibility. However, it should be noted that a logical objection could be raised against both relativity and quantum mechanics. After all, these theories have revolutionized nuclear physics and microelectronics. Thus, the discovery of a complete unified theory may not contribute to survival, and may not even affect the course of our lives. However, Even in the early days of civilization, people disliked unexplained and unconnected events, and they passionately desired to understand the order underlying our world. To this day, we dream of knowing why we are here and where we came from. Humanity's quest for knowledge is a sufficient justification for us to continue our search, and our ultimate goal is nothing less than a complete description of the universe in which we reside. Our modern understanding of the laws of motion of bodies traces back to Galileo and Newton. Before them, Aristotle's viewpoint prevailed, which held that the natural state of any body is rest. The laws governing the universe could be derived purely theoretically, with no need to test them experimentally. Therefore, for a long time, no one questioned whether bodies of different weights fall at different rates. It is said that Galileo demonstrated the falsity of Aristotle's doctrine by dropping bodies of different weights from the Leaning Tower of Pisa. This is almost certainly a fabrication, but Galileo did indeed perform similar experiments. He rolled balls of different weights down a smooth incline. Such an experiment is analogous to dropping heavy bodies from a tower, but it is simpler to observe since it involves lower speeds. Galileo showed that the speed of any body increases according to the same law, regardless of the body's weight. For example, if you take a ball and let it roll down a slope with a gradient of 1 meter for every 10 meters, no matter how heavy the ball is, the speed at the end of the first second will be 1 meter per second. At the end of the second second, it will be 2 meters per second, and so on. Of course, lead weights will fall faster than a feather, but only because the feather is more significantly slowed down by air resistance than the weights. If you drop two objects for which air resistance is minimal, such as two lead weights of different masses, they will fall at the same speed. Newton derived his laws of motion based on measurements conducted by Galileo. In Galileo's experiments, the same force, weight, always acted on an object rolling down an inclined plane, resulting in a constant increase in the object's speed. This indicated that the force applied to an object changes its speed rather than simply causing it to move, as was previously thought. It also meant that if no force acts on an object, it will move in a straight line at a constant speed. This idea was clearly articulated for the first time by Newton in his book Mathematical Principles, published in 1687. This law is now known as Newton's first law. The second law of Newton describes what happens to an object when a force acts on it. It states that an object will accelerate, meaning it will change its speed in proportion to the magnitude of the force. For example, if the force doubles, the acceleration will also double. Additionally, acceleration decreases as mass increases, meaning the amount of matter in the object. When the same force acts on an object with double the mass, it produces half the acceleration. Everyone is familiar with examples regarding cars. The more powerful the engine, the greater the acceleration it produces, but the heavier the car, the less acceleration the same engine provides. Besides the laws of motion, Newton discovered the law governing gravitational force. This law states that every object attracts any other object with a force proportional to the masses of those objects. Therefore, if the mass of one of the objects, say object A, is doubled, the force acting between the objects will also double. We consider this because the new object A can be thought of as composed of two objects, each with the original mass. Each of these objects would attract object B with a force equal to the original force. Consequently, the total force acting between objects A and B would be twice that original force. If one of the objects had a mass, say, twice as much, and the other 3 times the original mass, the interaction force would increase sixfold. Now, it is clear why all objects fall at the same speed. An object with double the weight will pull down with double the gravitational force, but its mass will also be twice as much. According to Newton's second law, these two effects cancel each other out, resulting in the same acceleration in all cases. Newton's law of gravitation states that the further apart two objects are, the weaker their interaction force. According to this law, the gravitational force of a star is exactly 1/4 of the gravitational force of a similar star located at half the distance. Newton's law allows for precise predictions of the orbits of the Earth, Moon, and planets. If the law of universal gravitation were different and gravitational forces decreased faster than Newton's law suggests, the orbits of the planets would be spirals converging towards the Sun. If gravitational attraction decreased with distance, the attraction of distant stars would appear stronger than that of the Earth. Aristotle's views differed significantly from those of Galileo and Newton, in that Aristotle considered a state of rest as a preferred state in which an object should always be if no force or impulse acts upon it. In particular, he believed that the Earth is at rest. However, Newton's laws imply that there is no single standard of rest. You could equally claim that object A is at rest, even if it is moving relative to object B at a constant speed, or that object B is at rest while object A is moving. For example, if we temporarily forget about our planet's rotation around its axis and its movement around the Sun, we could say that the Earth is at rest while a train is moving north at a speed of 90 kilometers per hour, or that the train is stationary while the Earth is moving south beneath it at the same speed. If someone on that train were to experiment with moving objects, they would find that all of Newton's laws hold true. For instance, playing table tennis on the train, you would find that the trajectory of the ball follows Newton's laws just as it would if you were playing on a stationary table, and you would not be able to tell which is moving, the train or the Earth. The absence of absolute rest means that it is impossible to determine whether two events occurred at the same point in space if it is known that they occurred at different times. For example, let's say our tennis ball in a moving train bounces off the table vertically upwards and, falling down, moves away after 1 second. To someone standing by the railway track, it would appear that the points of contact of the ball with the table are separated by a distance of about 40 meters, which the train has traveled during the time between the bounces. Therefore, the absence of an absolute state of rest means that no event can be assigned an absolute position in space, as Aristotle believed. The positions of events in space and the distances between them must differ for observers moving relative to each other, and there is no basis to claim that the position recorded by one observer is more preferable than that recorded by another. Newton was greatly troubled by the absence of an absolute position in space, or what was called absolute space, because it contradicted his idea of an absolute God. He effectively refused to accept the absence of absolute space, even though such an absence followed from the laws he himself had discovered. Many sharply criticized Newton for his irrational stubbornness, particularly Bishop Berkeley, a philosopher who believed that all material objects, as well as space and time, are illusions. Upon learning of Berkeley's views, the famous Dr. Johnson exclaimed, "I refute it," and stomped his foot on a large rock, nearly losing his balance. Both Aristotle and Newton believed in absolute time. In other words, they thought that the time interval between two events could be measured unambiguously, and that the result would be the same regardless of who was measuring, as long as the measurers had accurate clocks. Time was completely separate from space and considered independent of it. This was the viewpoint of the majority, the common sense perspective. However, we had to change our understanding of space and time, which was based on common sense. The two words in quotation marks refer to relatively slow objects, an apple, a planet, but they become completely inappropriate when speeds approach that of light. The fact that light travels at a finite, albeit very large speed, was established in 1676 by the Danish astronomer Ole Rømer. He discovered that the moments of the passage of Jupiter's moons across its disk do not follow at equal intervals, as they should if the moons revolve around Jupiter at a constant speed. As the Earth and Jupiter rotate around the Sun, the distance between these two planets changes. Rømer noted that the eclipses of Jupiter's moons are delayed more the further away we are from it. He explained this by stating that light from the moons takes longer to reach us when we are farther away. However, Rømer did not measure the change in distance from the Earth to Jupiter very accurately, and therefore the value he obtained for the speed of light was 140,000 miles per second, whereas the modern value is 186,000 miles per second. 1 mile equals 1.609 thousandths of a kilometer. The modern value of the speed of light is 290,450,008 meters per second. Nevertheless, Rømer's achievement was remarkable, as he not only proved that light travels at a finite speed, but also measured it, and he did all this 11 years before Newton's Mathematical Principles was published. A true theory of light propagation did not exist until 1018, when the English physicist James Clerk Maxwell managed to unify two private theories that were then used to describe electric and magnetic forces. According to Maxwell's equations, waves can exist in an electromagnetic field made up of two fields, similar to disturbances that propagate at a constant speed, like waves on the surface of a pond. If the wavelength, or the distance between the crests of adjacent waves, is 1 meter or more, we are dealing with radio waves. Shorter waves are called ultra-high frequency waves if their length is on the order of centimeters, and infrared waves if they are up to 10,000ths of a centimeter. The wavelength of visible light is only 480 millionths of a centimeter. Even shorter are the waves of ultraviolet, X-ray, and gamma radiation. Maxwell's theory predicted that radio waves and light should propagate at a fixed speed, but since Newton's theory put an end to the notion of absolute rest, when speaking of a fixed speed of light, it was necessary to specify relative to what this fixed speed is measured. In this context, the existence of a substance called ether was postulated, which filled everything, even the so-called empty space. Light waves propagate in the ether just as sound waves do in air, and therefore their speed is the speed relative to the ether. Observers moving at different speeds relative to the ether should see light approaching them at different speeds, but the speed of light relative to the ether should remain unchanged. In particular, since the Earth moves in the ether along its orbit around the Sun, the speed of light measured in the direction of the Earth's motion should exceed the speed of light measured perpendicular to the direction of motion, that is, when we are not moving towards the source. In 1887, Albert Michelson, who later became the first American to win the Nobel Prize in Physics, and Edward Morley conducted a very precise experiment at the Cleveland School of Applied Science. Michelson and Morley compared the values of the speed of light measured in the direction of the Earth's motion with its value measured in a perpendicular direction. To their immense surprise, they found that the measurements were exactly the same. From 1887 to 1905, a series of attempts were made, the most notable of which belonged to the Danish physicist Hendrik Lorentz, to explain the results of the Michelson-Morley experiment by suggesting that all objects moving in the ether shrink in size and that all clocks slow down. However, in 1905, an unknown clerk at the Swiss Patent Office named Albert Einstein published a paper that later became famous, demonstrating that no ether is needed if one abandons the concept of absolute time. Within a few weeks, the same viewpoint was expressed by one of the leading French mathematicians, Henri Poincaré. Einstein's arguments were closer to physics than Poincaré's, who approached the problem mathematically. Einstein is often referred to as the creator of a new theory, but Poincaré's name is also associated with the development of an important part of the fundamental postulate of this theory of relativity. The essence of the new theory is that the laws of science must be the same for all freely moving observers, regardless of their speed. This postulate was valid for Newton's laws of motion, but it was now extended to Maxwell's theories and the speed of light. The speed of light, as measured by any observers, must be the same regardless of the speed at which the observers themselves are moving. From this simple principle, a number of remarkable consequences follow. The most famous of these is probably the equivalence of mass and energy, expressed in Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light, and the law stating that nothing can move faster than light. Due to the equivalence of mass and energy, the energy possessed by a moving object must now be added to its mass. In other words, the more energy an object has, the harder it becomes to increase its speed. However, this effect is significant only at speeds close to the speed of light. For example, if an object's speed is 10% of the speed of light, its mass is only 0.5% greater than normal, whereas at a speed equal to 90% of the speed of light, the mass already exceeds normal by 2 times. As the speed of an object approaches the speed of light, its mass increases more rapidly, requiring more and more energy for further acceleration. In fact, an object's speed can never reach the speed of light, as its mass would become infinitely large, and since mass is equivalent to energy, achieving such a speed would require infinitely large energy. Thus, any normal object, due to the principle of relativity, is forever doomed to move at a speed not exceeding the speed of light. Only light and other waves that do not possess mass can travel at the speed of light. Another remarkable consequence of the postulates of relativity is the revolution in our understanding of space and time. According to Newton's theory, if a light pulse is sent from one point to another, the time it takes to travel will be the same for different observers, since time is absolute. But the distance it travels may differ for different observers, because space is not absolute. And since the speed of light, that is, the distances traveled by light divided by time, differs, observers will receive different speeds of light. In the theory of relativity, however, all observers must agree on the speed at which light propagates, and since they do not agree on the distance traveled by light, they should not agree on how long the light took. The time of travel is the distance traveled by light, for which there is no agreement among observers, divided by the speed of light, which all agree on. In other words, the theory of relativity has put an end to the concept of absolute time. It turned out that each observer must have their own timescale, measured using their own clocks, and that the readings of identical clocks held by different observers do not necessarily agree. Each observer can determine where and when an event occurred by using radar, sending a light pulse or a radio signal. Part of the sent signal will reflect back at the end of its path, and the observer will measure the time of return of the echo signal. The time of the event will be the midpoint of the interval between sending the signal and its return. The distance to the event is equal to half the time taken for the round trip multiplied by the speed of light. Here, an event is understood as something occurring at a specific point in space at specific moments in time. Using the method described, observers moving relative to each other attribute different times and positions in space to the same event. None of the measurements made by different observers will be more correct than others, but all will be interrelated. Each observer can accurately calculate what time and position in space any other observer will assign to an event if the speed of the second observer relative to the first is known. For accurate distance determination, this method is now used because we can measure time more precisely than length. Even the meter is defined as the distance light travels in 0.08, 0.649 thousandths of a second, measured using cesium. This number corresponds to the historical definition of a meter as the distance between two marks on a special platinum rod stored in Paris. We can also use a more convenient new unit of length called the light second. This is simply the distance light travels in 1 second. In the theory of relativity, distance is now defined through time and the speed of light, from which it automatically follows that measuring the speed of light, every observer will obtain the same result. By definition, 1 meter equals 0.080,335 thousandths, 649 thousandths of a second. There is no longer a need to introduce ether, the presence of which, by the way, as demonstrated by the Michelson-Morley experiment, cannot be detected. However, the theory of relativity forces us to fundamentally change our understanding of space and time. We must accept that time is not completely separate from space and is not independent of it, but together with it forms a single object called spacetime. From everyday experience, we know that the position of a point in space can be specified by 3 numbers, its coordinates. For example, one could say that a certain point in a room is 2 meters from one wall, 1 meter from another, and 1.5 meters from the floor. Or one could specify its position by indicating latitude, longitude, and height above sea level. You can use any 3 suitable coordinates, although they always have only a limited range of applicability. No one would, when specifying the position of the moon, indicate distances in kilometers north and west from Piccadilly Circus and height above sea level. Instead, one could specify the distance to the sun, the distance to the plane in which the orbits of the planets lie, and the angle between the line connecting the Moon to the Sun and the line connecting the Sun to some nearby star, say Alpha Centauri. However, even these coordinates are unlikely to be suitable for specifying the position of the Sun in our galaxy, or the position of our galaxy among the surrounding galaxies. But one can divide the entire universe into overlapping pieces and introduce a coordinate system for each piece to specify the position of a point within it. An event is something that occurs at a specific point in space at a specific moment in time. Therefore, events can be characterized by specifying the position of a point on the surface of the Earth, measuring in kilometers the distances to it to the north and west of Piccadilly Circus. One could also measure the distance from the same Piccadilly Circus, but to the northeast. The four coordinates of any event can be viewed as coordinates defining the position of that event in a four-dimensional space known as spacetime. A four-dimensional space is impossible to visualize. Personally, I find it difficult to even visualize three-dimensional space, but it is not hard to graphically represent two-dimensional space, such as the surface of the Earth. The surface of the Earth is two-dimensional because the position of any point can be specified with two coordinates, latitude and longitude. The time axis is directed upwards, and one of the spatial axes is horizontal. The other two spatial dimensions will either be absent, or one of them I will sometimes depict in perspective. The time axis is directed upwards, and the scale is measured in years, while the distance from the Sun to the star Alpha Centauri is plotted along the horizontal axis and measured in miles. We have seen that Maxwell's equations predict the constancy of the speed of light regardless of the speed of the source, and these predictions are confirmed by precise measurements. Thus, a light pulse emitted at a certain moment from a certain point in space will spread out over time in all directions, forming a light sphere whose size and position depend on the speed of the source. After 1/1,000,000th of a second, light forms a sphere with a radius of 300 meters. After 2/1,000,000ths of a second, the radius of the sphere will increase to 600 meters, and so on. The picture will resemble waves on water spreading across the surface of a pond from a thrown stone. These waves spread out like a circle, expanding over time. If we imagine a three-dimensional model where two dimensions are on the surface of the pond and one is in time, in such a model, the expanding circle on the water will represent a cone, the vertex of which was at the moment the stone fell at the point on the surface of the pond where the stone touched the water. Similarly, light, spreading from a certain event in four-dimensional spacetime, forms a three-dimensional cone within it. This cone is called the light cone of the future for that event. One can also draw another cone, called the light cone of the past, which represents the set of events from which a light pulse could reach the point corresponding to that event. The light cones of the past and future for a given event R divide spacetime into three regions: the region of the past, the region of the present, and the region of the future of that event. The area enclosed within the light cone of the future event R is the set of all events that can, in principle, be influenced by what happens at point R. Events lying outside the light cone of event R are unreachable by signals emanating from point R, since nothing can move faster than light. Therefore, they are not affected by what occurs at point R. The absolute past event R lies within the light cone of the past. This is the set of all events whose signals, propagating at the speed of light or slower, can reach point R. Thus, the light cone of the past contains the set of all events that can influence events at point R. Knowing what happens at a certain moment in time, everywhere in the region of space bounded by the light cone of the past event R, one can predict what must occur at point R itself. The region of space not lying within the light cones of the past and future will be called the external region. Events approaching the external region cannot influence events at point R, nor be influenced by events occurring at R. For example, if the sun were to suddenly stop shining right now, it would not affect life on Earth at this moment, as we would still be in the external region relative to the point where the sun has gone out, and we would only learn about it after 8 minutes, the time it takes for light from the sun to reach the Earth. Only then would events occurring on Earth fall within the light cone of the future of the point where the sun has gone out. For the same reason, we do not know what is happening far away in the universe at this moment. The light that has reached us from distant galaxies was emitted 1,000,000 years ago, and light from the most distant observable object has been traveling to us for 8,000 million years. This means that when we look at the sky in the universe, we see it in the past. If we disregard gravitational effects, as Einstein and Poincaré did in 1905, we arrive at what is called the special or private theory of relativity. For each event in spacetime, we can construct a light cone representing the set of all possible paths along which light emitted from the point spreads. Since the speed of light is the same for any event and in any direction, all light cones will be identical and oriented in the same direction. Furthermore, this theory tells us that nothing can move faster than light. This means that the trajectory of any object in time and space must be represented as a line lying within the light cones for all events along it. The special theory of relativity allowed for an explanation of the constancy of the speed of light for all observers, established in the Michelson-Morley experiment, and accurately described what happens when moving at speeds close to the speed of light. However, the new theory contradicted Newton's theory of gravity, according to which objects attract each other with a force that depends on the distance between them. This implies that if one of the objects is moved, the force acting on the other changes instantly. In other words, the speed of the propagation of gravitational effects must be infinite. They are equal to or less than the speed of light, as required by the special theory of relativity. From 1908 to 1914, Einstein made a series of unsuccessful attempts to construct a model of gravity that would be consistent with the special theory of relativity. Finally, in 1915, he published a theory now called the general theory of relativity. Einstein proposed a revolutionary hypothesis. Gravity is not an ordinary force, but a consequence of the fact that space-time, previously thought to be flat, is curved by the mass and energy distributed within it. Bodies such as the Earth do not need to move along curved orbits due to gravitational force. They move along lines that correspond most closely to straight lines in ordinary space and are called geodesics. A geodesic is the shortest and straightest path between two neighboring points. For example, the surface of the Earth is a curved two-dimensional space. The geodesic on Earth is a great circle, which is the shortest path between 2 points, as the shortest route between 2 airports along the geodesic is always the one designated by dispatchers to pilots. According to the general theory of relativity, bodies always move along straight lines in four-dimensional spacetime, but we see them moving along curved trajectories in our three-dimensional space. A pilot flying a plane over hilly terrain is flying in a straight line in three-dimensional space, while their shadow moves along a curve on the two-dimensional surface of the Earth. The mass of the Sun curves spacetime so that, although the Earth moves in a straight line in four-dimensional space, we see it moving in a circular orbit in our three-dimensional space. The orbits of planets predicted by the general theory of relativity nearly coincide with the predictions of Newton's theory of gravitation. However, in the case of Mercury, which, being the closest planet to the Sun, experiences the strongest gravitational effects and has a rather elongated orbit, the general theory of relativity predicts that the major axis of the ellipse can rotate around the Sun by about 1 degree every 10,000 years. Despite its smallness, this effect was observed even before 1915 and was considered one of the confirmations of Einstein's theory. In recent years, radar methods have measured even smaller deviations of the orbits of other planets from Newton's predictions, and they agree with the predictions of the general theory of relativity. Light rays must also follow geodesics in spacetime. The curvature of space means that light does not propagate in a straight line. Thus, according to the general theory of relativity, a light ray must bend in gravitational fields. For example, the light cones of points near the Sun should be slightly deformed by the Sun's mass. This means that a light ray from a distant star passing near the Sun should be deflected at a small angle, and an observer on Earth would see that star in a different position. Of course, if the light from a given star always passed near the Sun, we would not be able to tell whether the light ray is deflected or if the star is indeed located where we see it. However, due to the Earth's rotation, new stars continually pass behind the solar disk, and their light is deflected. As a result, their apparent position relative to other stars changes. Under normal conditions, this effect is very difficult to observe, as the bright sunlight makes it impossible to see stars located near the Sun. Such an opportunity arises during a solar eclipse when the moon blocks sunlight. In 1915, no one was able to immediately verify Einstein's predicted deflection of light because World War I was underway. It was only in 1919 that an English expedition in West Africa, which observed a solar eclipse there, demonstrated that light is indeed deflected by the Sun, as Einstein had predicted. The theory that English scientists proved the validity of a theory originating from Germany was welcomed as another great act of reconciliation between the two countries after the war. However, although this seems ironic, a later analysis of photographs obtained during these expeditions revealed measurement errors of the same order as the effect being measured. The English results were either pure luck or one of those rare cases in science where one gets what one hoped to obtain. However, the deflection of light by the Sun was subsequently confirmed by a number of observations. Another prediction of the general theory of relativity is that time should flow more slowly near a massive body like Earth. This follows from the requirement that a certain relationship must hold between the energy of light and its frequency, that is, the number of light waves per second. The greater the energy, the higher the frequency. If light travels upward in Earth's gravitational field, it loses energy, and therefore its frequency decreases. This means that the time interval between the crests of two adjacent waves increases. An observer positioned at a high altitude should perceive that everything below is happening more slowly. This prediction was tested in 1962 using two very precise clocks, one located at the top of a water tower and the other at its base. It turned out that the lower clock, which was closer to the Earth, ran slower, in exact accordance with the general theory of relativity. The difference in the rate of clocks at different heights above the Earth's surface has now gained enormous practical significance with the advent of very precise navigation systems that operate on signals from satellites. If the predictions of the general theory of relativity are not taken into account, the coordinates will be calculated with an error of several kilometers. Newton's laws of motion put an end to the concept of absolute position in space, while the theory of relativity freed us from absolute time. Consider a pair of twins. Suppose one of them goes to live on a mountaintop, while the other stays at sea level. The first will age faster than the second, so when they meet, one will appear older than the other. The age difference would be quite small, but it would increase significantly if one of the twins embarked on a long journey in a spaceship traveling at a speed close to that of light. Upon returning, he would be significantly younger than his brother who remained on Earth. This is known as the twin paradox, but it is only a paradox for those who deep down believe in absolute time. In the general theory of relativity, there is no single absolute time. Each individual has their own time scale, dependent on where that individual is and how they are moving. Until 1915, space and time were perceived as a rigid arena for events, unaffected by anything that happened within it. This was even the case in the special theory of relativity. Bodies moved, forces attracted and repelled, but time and space simply remained as they were, unaffected. For you naturally think that space and time are infinite and eternal. In the general theory of relativity, however, the situation is completely different. Space and time are now dynamic quantities. When a body moves or a force acts, it changes the curvature of space and time, and the structure of space-time, in turn, affects how bodies move and how forces act. Space and time influence everything that happens in the universe, but they also change under the influence of everything occurring within it. Just as one cannot speak of events in the universe without a concept of space and time, it has become meaningless in the general theory of relativity to speak of space-time beyond the universe. The following decade was set to revolutionize our views of the universe with this new understanding of space and time. Old notions of an almost unchanging universe that may have always existed and will exist forever were replaced by a picture of a dynamic, expanding universe that seemingly emerged at some point in the past and may eventually cease to exist in the future. On a clear moonless night, if you look up at the sky, the brightest objects you are likely to see will be the planets: Venus, Mars, Jupiter, and Saturn. Additionally, you will see a vast number of stars resembling our Sun, but located much farther from us. As the Earth orbits the Sun, some of these so-called fixed stars slightly change their positions relative to one another, meaning they are not truly fixed. The fact is that they are somewhat closer to us than others. As the Earth rotates around the Sun, nearby stars are seen at different points against the background of more distant stars. This allows us to directly measure the distances to these stars. The closer they are, the more noticeable their movement. The closest star, called Proxima Centauri, is approximately 4 light years away from us, meaning light from it takes about 4 years to reach Earth, or about 37 trillion kilometers. Most stars visible to the naked eye are several hundred light years away. Compare this to the distance to our Sun, which is 8 light minutes away. Visible stars are scattered across the night sky, particularly densely in the band we call the Milky Way. As early as 1750, some astronomers suggested that the existence of the Milky Way could be explained by the fact that most visible stars form a disk-like configuration, an example of what is now called a spiral galaxy. It was only several decades later that astronomer William Herschel confirmed this hypothesis by conducting an enormous effort to compile a catalog of the positions of a vast number of stars and their distances. Even after that, the concept of spiral galaxies was accepted by all only at the beginning of our century. The modern picture of the universe only emerged in 1924, when American astronomer Edwin Hubble showed that our galaxy is not the only one. In fact, there are many other galaxies separated by vast regions of empty space. To prove this, Hubble needed to determine the distances to these galaxies, which are so vast that unlike the positions of nearby stars, the apparent positions of galaxies do not change. Therefore, to measure distances, Hubble was forced to use an indirect method. The apparent brightness of a star depends on two factors: the amount of light emitted by the star and its distance from us. We can measure the brightness of nearby stars and their distances. Therefore, we can calculate their luminosity. Conversely, knowing the luminosity of stars and other galaxies, we could calculate their distance by measuring their apparent brightness. Hubble noticed that the luminosity of certain types of stars is always the same when they are close enough for measurements to be made. Therefore, Hubble reasoned, if such stars are found in another galaxy, by assuming they have the same luminosity, we can calculate the distance to that galaxy. If similar calculations for several stars in the same galaxy yield the same result, the obtained distance estimate can be considered reliable. In this way, Hubble calculated the distances to 9 different galaxies. It is now known that our galaxy is one of several 100 billion galaxies observable with modern telescopes, and each of these galaxies, in turn, contains hundreds of billions of stars. Our galaxy is about 100,000 light-years in diameter. It rotates slowly, and the stars in its spiral arms make approximately 1 complete revolution around its center every few 100 million years. Our Sun is an ordinary yellow star of average size, located on the inner side of one of the spiral arms. What a vast journey we have made since Aristotle and Ptolemy, when Earth was considered the center of the universe. The stars are so far away from us that they appear merely as glowing points in the sky. We cannot distinguish their sizes and shapes. How then can we speak of different types of stars? For the vast majority of stars, there is only one characteristic property that can be observed. This is the color of the light they emit. Newton discovered that when sunlight passes through a triangular piece of glass, called a prism, it disperses, like in a rainbow, into its light components, the spectrum. By adjusting a telescope to a particular star or galaxy, one can similarly disperse the light emitted by that star or galaxy into a spectrum. Different stars have different spectra, but the relative brightness of different colors is always exactly the same as in the light emitted by a hot object. The light emitted by a hot, opaque object has a very characteristic spectrum that depends only on the temperature of the object, a thermal spectrum. Therefore, we can determine the temperature of a star from the spectrum of light it emits. Additionally, we will find that some very specific colors are completely absent from the spectra of stars, and the absent colors differ for different stars since, as we know, each chemical element absorbs its own specific set of characteristic colors. We can compare these with the colors that are absent from the spectrum of a star, thus accurately determining which elements are present in its atmosphere. In the 1920s, when astronomers began studying the spectra of stars in other galaxies, something even stranger was discovered. In our own galaxy, the same characteristic sets of absent colors were found as in the stars, but all were shifted by the same amount towards the red end of the spectrum. To understand the significance of this, one must first grasp the Doppler effect. As we already know, visible light consists of oscillations or waves of electromagnetic fields. The frequency, numerically equal to the number of light oscillations per second, is extremely high, ranging from 400 to 700 million waves per second. The human eye perceives light of different frequencies as different colors, with the lowest frequencies corresponding to the red end of the spectrum and the highest to the violet. Imagine a light source located at a fixed distance from us. For example, a star emitting light waves at a constant frequency. Obviously, the frequency of the incoming waves will be the same as that with which they are emitted. Let's assume the gravitational field of the galaxy is small, and its influence is negligible. Now suppose the source begins to move towards us. As it emits the next waves, the source will be closer to us, and thus the time it takes for the crest of these waves to reach us will be less than if the star were stationary. Therefore, the time between the crests of two incoming waves will be shorter, and the number of waves we receive in 1 second, that is, the frequency, will be greater than when the star was stationary. Conversely, when the source is moving away, the frequency of the incoming waves will be lower. This means that the spectra of receding stars will be shifted towards the red end, redshift, while the spectra of approaching stars should experience a blue shift. This relationship between speed and frequency is called the Doppler effect, and this effect is common even in our daily lives. Listen to how a car moves down the highway. As it approaches, the engine sound is higher, meaning the frequency of the sound waves it emits is higher, and when it passes by and begins to move away, the sound becomes lower. Light waves and radio waves behave in a similar manner. The police use the Doppler effect to determine the speed of cars from a distance based on the frequency of radio signals reflected from them. After proving that other galaxies exist, Hubble dedicated the following years to compiling catalogs of distances to these galaxies and observing their spectra. At that time, most scientists believed that the movement of galaxies was random, and therefore the spectra shifted towards red should be observed as frequently as those shifted towards blue. How surprising it was when redshift spectra were found in the majority of galaxies, meaning that almost all galaxies are moving away from us. Even more astonishing was the discovery published by Hubble in 1929. Hubble found that the magnitude of the redshift is not random, but directly proportional to the distance from us to the galaxy. In other words, the farther away a galaxy is, the faster it is receding. This meant that the universe could not be static, as previously thought. In reality, it is continuously expanding, and the distance between galaxies is constantly increasing. The discovery of the expanding universe was one of the great intellectual revolutions of the 20th century. In hindsight, we can only marvel at the fact that this idea did not occur to anyone earlier. Newton and other scientists should have realized that a static universe would soon begin to collapse under the influence of gravity. But suppose the universe is expanding instead. If the expansion were to occur slowly enough, the gravitational forces would eventually halt it. The idea shifted to contraction. However, if the expansion speed exceeds a certain critical value, gravitational interaction would not be sufficient to stop the expansion, and it would continue indefinitely. All this is somewhat reminiscent of the situation that arises when a rocket is launched upwards from the surface of the Earth. If the rocket's speed is not very high, due to gravity, it will eventually stop and begin to fall back. However, if the rocket's speed exceeds a certain critical value, around 11 kilometers per second, the gravitational force will not be able to bring it back, and the rocket will continue its motion away from the Earth forever. The expansion of the universe could have been predicted based on Newtonian gravity theory in the 18th and even late 17th century. However, the belief in a static universe was so strong that it persisted even into the early 20th century. Even Einstein, while developing the general theory of relativity in 1915, was convinced of the universe's static nature. To avoid contradicting this static view, he ultimately modified his theory by introducing what is known as the cosmological constant into the equation. He introduced a new anti-gravitational force that, unlike other forces, was not generated by any source, but was embedded in the very structure of space-time. Einstein argued that space and time themselves are always expanding, and this expansion precisely counterbalances the attraction of all other matter in the universe, resulting in a static universe. Apparently, only one person fully believed in the general theory of relativity. While other physicists pondered how to circumvent the non-static universe predicted by this theory, Russian physicist and mathematician Friedmann, on the contrary, focused on explaining it. Friedmann made two very simple initial assumptions. First, the universe looks the same regardless of the direction from which we observe it. And second, this statement should remain true even if we were to make observations from some other location. Without resorting to any other assumptions, Friedmann showed that the universe should not be static. In 1922, a few years before Hubble's discovery, Friedmann precisely predicted his result. The assumption of uniformity in the universe in all directions does not hold true in reality. For example, as we already know, other stars in our galaxy form a clearly defined bright band that stretches across the night sky, the Milky Way. However, when it comes to distant galaxies, the number in all directions is approximately the same. Therefore, the universe indeed appears roughly uniform in all directions when observed on a scale large compared to the distances between galaxies, when small-scale differences are disregarded. For a long time, this was the only justification for Friedmann's hypothesis as a rough approximation of the real universe. But then, by chance, it turned out that Friedmann's hypothesis indeed provides an astonishingly accurate description of our universe. In 1965, two American physicists, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, we're testing a very sensitive microwave detector. Microwaves are the same as light waves, but their frequency is only 10,000 million in the range. Penzias and Wilson noticed that the noise level registered by their detector was higher than it should have been. This noise was not directional, coming from any specific side. Initially, the researchers found bird droppings in the detector and attempted to explain the effect through other similar causes, but eventually, all such factors were ruled out. They knew that any noise coming from the atmosphere is always stronger when the detector is pointed directly upwards, and when it is tilted, since light rays coming from the horizon pass through significantly thicker layers of the atmosphere than rays hitting the detector directly from above. Only below is the noise the same, regardless of where the detector is pointed. Therefore, the source of the noise must be located beyond the atmosphere. The noise was consistent both day and night, and throughout the year, despite the fact that the Earth rotates on its axis and continues its orbit around the Sun. This meant that the radiation source is located beyond the solar system and even beyond our galaxy, for otherwise, the intensity of the radiation would have changed due to the Earth's movement altering the detector's orientation. As we know, the radiation travels almost through the entire observable universe on its way to us. Given that it is uniform in all directions, it means the universe itself is uniform in all directions, at least on a large scale. We now know that no matter which direction we observe, this noise varies by no more than 1/10,000th. Thus, Penzias and Wilson, unknowingly, provided remarkably precise confirmation of Friedmann's first assumption. Around the same time, two American physicists from the nearby Princeton University, Bob Dickey and Jim Peebles, were also investigating microwaves. They were testing the hypotheses of George Gamow, a former student of Friedmann, that the early universe was very hot, dense, and glowing white-hot. Dickey and Peebles suggested that we might see the glow of the early universe, as light emitted from very distant regions could only reach us now. But due to the expansion of the universe, the redshift of the light spectrum must be so great that the light reaching us would already be microwave radiation. Dickey and Peebles were preparing to search for such radiation when Penzias and Wilson, upon learning about Dickey and Peebles's work, realized they had already found it. For this experiment, Penzias and Wilson were awarded the Nobel Prize in 1978, which was somewhat unfair considering Dickey and Peebles, not to mention Gamow. At first glance, the fact that the universe appears the same in all directions might suggest some uniqueness to our location in the universe. In particular, since we see that all other galaxies are moving away from us, it seems we are at the center of the universe. However, there is another explanation. The universe would appear uniform in all directions, even if viewed from some other galaxy. This, as we know, is Friedmann's second hypothesis. We have no scientific evidence for or against this assumption, and we accepted it, so to speak, out of modesty. It would be extremely strange if the universe appeared uniform in all directions only around us, while being different at other points. In Friedmann's model, all galaxies are receding from one another. It is somewhat like an inflated balloon on which points are drawn. As it is inflated further, the distance between any two points increases, but none can be called the center of expansion. Moreover, the greater the distance between points, the faster they recede from one another. However, in Friedmann's model, the speed at which any two galaxies recede from each other is proportional to the distance between them. Thus, Friedmann's model predicts that the redshift of a galaxy should be directly proportional to its distance from us, in exact accordance with Hubble's discovery. Despite the success of this model and its predictions aligning with Hubble's observations, it remained unknown in the West until 1935, when American physicist Howard Robertson and English mathematician Arthur Walker proposed similar models. In connection with Hubble's discovery, Friedmann considered only one model, but three different models can be indicated for which both fundamental assumptions of Friedmann hold true. In the first type of model, discovered by Friedmann himself, the universe expands slowly enough that due to gravitational attraction between different galaxies, the expansion of the universe slows down and eventually stops. After this, the galaxies begin to come closer together, and the universe starts to contract. How does the distance between two neighboring galaxies change over time? It increases from 0 to some maximum, and then again falls to 0. In the second type of model, the expansion of the universe occurs so rapidly that gravitational attraction, although it slows down the expansion, cannot stop it. The curve rises from 0, and eventually galaxies recede from each other at a constant speed. Finally, there is a third type of model in which the speed of expansion of the universe is just enough to avoid collapsing to 0. In this case, the distance between galaxies also starts at 0 and then continuously increases. However, the galaxies recede at an ever-decreasing speed, but it never falls to 0. The first type of Friedmann's model is remarkable in that the universe is not infinite in space. Although space has no boundaries, gravity is so strong that space curves back on itself, resembling the surface of the Earth. Indeed, when moving in a certain direction on the surface of the Earth, you will never encounter an insurmountable barrier, nor will you fall off the edge, and eventually you will return to the same point from which you started. In Friedmann's first model, space is similar, but instead of 2 dimensions, the surface of the Earth has 3 dimensions. The fourth dimension, time, also has a finite extent, but it is like a segment of a line with a beginning and an end. Later, we will see that if the general theory of relativity is combined with quantum mechanics and the uncertainty principle, it turns out that both space and time can be finite without having any edges or boundaries. The idea that one could travel around the universe and return to the same place is suitable for science fiction, but has no practical significance, as it can be shown that the universe would collapse to 0 before completing the journey. To return to the starting point before the end of the universe, one would have to move at a speed exceeding the speed of light, which is impossible. In Friedmann's first model, where the universe expands and contracts, space curves back on itself like the surface of the Earth, so its dimensions are finite. In the second model, where the universe expands infinitely, space is curved differently, like the surface of a saddle. Thus, in the second case, space is infinite. Finally, in the third model of Friedmann, with critical expansion speed, space is flat, hence also infinite. But which of Friedmann's models is suitable for our universe? Will the universe eventually stop expanding and begin to contract, or will it expand forever? To answer this question, we need to know the current rate of expansion of the universe and its average density. If the density is less than a certain critical value, depending on the rate of expansion, then gravitational attraction will be too weak to stop the expansion. If, however, the density is greater than critical, then at some point in the future, due to gravity, the expansion of the universe will cease and begin to contract. The current rate of expansion of the universe can be determined by measuring the velocities of other galaxies receding from us using the Doppler effect. Such measurements can be made very accurately, but the distance to other galaxies is poorly known because it cannot be measured directly. We only know that the universe expands by about 5 to 10% every 1,000 million years. However, the uncertainty in the current average density of the universe is even greater. If we sum the masses of all observable stars in our and other galaxies, even at the lowest estimate of the rate of expansion, the total will be less than 1/100th of the density required to halt the expansion of the universe. However, there must be a lot of dark matter in both our and other galaxies, which cannot be seen directly, but whose existence we infer from how its gravitational attraction affects the orbits of stars and galaxies. Additionally, galaxies are primarily observed in clusters, and we can similarly deduce the presence of even more intergalactic dark matter within these clusters, which influences the motion of galaxies. Summing the mass of all dark matter gives us only 1/10 of the amount necessary to stop the expansion. However, we cannot rule out the possibility of some other form of matter, evenly distributed throughout the universe and not yet detected, that could increase the average density of the universe to the critical value necessary to halt the expansion. Thus, the available data suggests that the universe will likely expand forever. The only thing we can be completely sure of is that if the contraction of the universe does occur, it will not happen any sooner than 10,000 million years from now, as it has already been expanding for at least that long. However, this should not trouble us too much. By that time, if we do not relocate beyond the solar system, humanity will have long ceased to exist. It will fade away along with the sun. All variants of Friedmann's model share the commonality that at some moment in the past, 10 to 20,000 million years ago, the distance between neighboring galaxies must have equaled 0. At this moment, referred to as the Big Bang, the density of the universe and the curvature of space-time must have been infinite. Since mathematicians do not know how to deal with infinitely large quantities, this means that according to the general theory of relativity, which underpins Friedmann's solution, there must be a singularity in the universe where this theory is not applicable. Such a singularity in mathematics is called a special one. All our scientific theories are based on the assumption that space-time is smooth and nearly flat, and therefore all these theories are invalid at the singular point of the Big Bang, where the curvature of space-time is infinite. Consequently, even if any events occurred before the Big Bang, they could not be used to predict the future, as at the point of the Big Bang, the possibilities for prediction would be reduced to 0. Similarly, we only know what happened after the Big Bang, and we know only this, but we will not be able to learn what occurred before it. Events that occurred before the Big Bang cannot have any consequences that concern us, and therefore should not be included in the scientific model of the universe. Consequently, they need to be excluded from the model, and the moment of the Big Bang should be considered the beginning of the measurement of time. The idea that time had a beginning is unappealing to many, possibly because it hints at the intervention of divine forces. At the same time, the Catholic Church embraced the Big Bang model and officially proclaimed in 1951 that it is consistent with the Bible. In this context, several attempts to do without the Big Bang have been made. The stationary universe model and its authors received the most support. In 1948, there were H. Bondi and Gold, who fled Nazi-occupied Austria, and the Englishman Hoyle, who worked with them on radar problems during the war. Their idea was that as galaxies move apart, new galaxies continuously form from newly created matter that fills the gaps. Therefore, the universe should appear roughly the same at all moments in time and in all points of space. Of course, some modifications to the theory of relativity were required for this continuous creation of matter, but the necessary creation rate turned out to be so small, 1 particle per cubic kilometer per year, that there were no contradictions with experiments. The stationary model is an example of a good scientific theory. It is simple and provides a definite prediction that can be tested through observations. One of its predictions is that the number of galaxies and other similar objects in any given volume of space should remain constant, regardless of when and where in the universe observations are made. At the end of the 1950s and the beginning of the 1960s, astronomers from Cambridge University, led by Ryle, who during the war also worked with Bondi and Gold on radar development, compiled a catalog of radio sources coming from outer space. This Cambridge group showed that most of these radio sources must lie outside our galaxy. Many sources could even be identified with other galaxies, and, in addition, there were far more weak sources than strong ones. Weak sources were interpreted as being more distant, while strong sources were considered to be closer. Furthermore, it turned out that the number of ordinary sources per unit volume in distant regions was greater than in closer areas. This could mean that we are located in the center of a vast region of the universe where there are fewer sources than in other places. But another explanation was also possible. In the past, when the radio waves began their journey to us, there were more sources than there are now. Both explanations contradict the predictions of the stationary universe theory. Additionally, the microwave radiation discovered in 1960 by Penrose and Wilson also indicated a greater density of the universe in the past, leading to the abandonment of the stationary universe model. In 1963, 2 Soviet physicists, Lifshitz and Vatnik, made another attempt to exclude the Big Bang and, with it, the beginning of time. Lifshitz and Vatnik suggested that the Big Bang is merely a feature of Friedmann models, which ultimately provide only an approximate description of the real universe. It is possible that among all the models that describe the existing universe to some extent, the singularity of the Big Bang point arises only in Friedmann models. According to Friedmann, all galaxies are receding directly from one another, and therefore they all were once at the same location. However, in the real universe, galaxies never move apart in a perfectly straight line. They usually have small velocity components directed at angles. Thus, in reality, galaxies do not need to be exactly at the same point. It is sufficient for them to be located very close to each other. Therefore, the currently expanding universe could have arisen not from the singular point of the Big Bang, but from some earlier phase of contraction. Perhaps galaxies collided with each other, and not all particles, but some fraction of them could have passed by one another and then separated again, resulting in the observed expansion of the universe. How, then, can we determine whether the Big Bang was the beginning of the universe? Lifshitz and Vatnik studied models that would broadly resemble Friedmann models, but differed from them by taking into account the irregularities and random nature of the actual velocities of galaxies in the universe. As a result, Lifshitz and Vatnik showed that in such models, the Big Bang could be the beginning of the universe, even if galaxies do not always recede in a straight line. However, this could only hold for a very limited range of models in which the motion of galaxies occurs in a specific way. Since there are infinitely more Friedmann-type models that do not contain the Big Bang than those that do contain such a singularity, Lifshitz and Vatnik argued that, in fact, there was no Big Bang. However, later they found a much broader class of Friedmann-type models that contain singularities and in which it is not necessary for galaxies to move in any particular way. Therefore, in 1970, Lifshitz and Vatnik abandoned their theory. Nevertheless, their work was of great importance, as it demonstrated that if the general theory of relativity is correct, then the universe could have a special point of the Big Bang. But this work did not answer the main question. Does the general theory of relativity imply that the universe must have had a beginning, the Big Bang? The answer to this question was obtained through a completely different approach proposed in 1960 by the English mathematician and physicist Roger Penrose. Based on the behavior of light cones in the general theory of relativity and the fact that gravitational forces are always attractive, Penrose showed that when a star collapses under the influence of its own gravitational forces, it is confined to a region whose surface ultimately shrinks to zero. And since the surface of this region shrinks to zero, the same must happen to its volume. All the matter of the star will be compressed into zero volume, making its density and the curvature of space-time infinite. In other words, a singularity arises in a certain region of space-time, known as a black hole. At first glance, this theorem by Penrose applies only to stars. It does not state whether the entire universe experienced a Big Bang in the past. I read Penrose's theorem, which states that any body undergoing gravitational collapse must ultimately shrink to a singular point. Soon I realized that if the direction of time in the theorem were reversed, so that the collapse turned into expansion, this theorem would still hold. Since the universe is currently at least roughly described on a large scale by the Friedmann model, according to Penrose's theorem, the final state of any collapsing star must be a singularity. When time is reversed, this theorem asserts that in any Friedmann model, the initial state of the expanding universe must also be a singularity. For technical reasons, the theorem by Penrose was introduced with the condition that the universe is infinite in space. Therefore, based on this theorem, I could only prove that a singularity must exist if the expansion of the universe occurs quickly enough to prevent a subsequent collapse, as only such Friedmann models exist in infinite space. We have seen how, in less than half a century, people's perceptions of nature, which had been formed over thousands of years, changed. This change was initiated by Hubble's discovery, the expansion of the universe, and the realization of our planet's insignificance amid the vastness of the universe. As experimental and theoretical results multiplied, it became increasingly clear that the universe must have had a beginning. From our proof, it followed that the general theory of relativity is an incomplete theory. It does not answer the question of how the universe originated, because according to the theory of relativity, all physical theories, including itself, break down at the point of the universe's origin. However, The general theory of relativity does not claim to be a complete theory. Theorems about singularities actually assert only that at some very early stage of development, the sizes of the universe were very small, so that at that time, very significant small-scale effects, which are addressed by another of the great theories of the 20th century, quantum mechanics, could be very relevant. Thus, in the early 1970s, we had to shift our research on the universe from the theory of the extremely large to the theory of the extremely small. Influenced by the success of scientific theories, especially Newton's theory of gravity, the French scientist Pierre-Simon Laplace developed a view of the universe as a completely deterministic object in the early 19th century. Laplace believed that there must exist a set of scientific laws that would allow one to predict everything that could happen in the universe, provided that a complete description of its state at any moment in time is known. For example, if we knew the positions of the sun and the planets at a certain moment, we could use Newton's laws to calculate the state of the solar system at any other moment. In this case, determinism is quite evident. But Laplace went further, asserting that similar laws exist for everything, including human behavior. The doctrine of scientific determinism encountered strong resistance from many who felt that it limited God's free intervention in our world. Nevertheless, this idea remained a common scientific hypothesis even at the beginning of our century. One of the first indications of the need to abandon determinism came from the results of calculations by two English physicists, John Rayleigh and James Jones, which suggested that a hot object like a star must continuously emit infinitely large amounts of energy. According to the known laws at the time, a hot body must emit electromagnetic waves of all frequencies equally, such as radio waves, visible light, and X-rays. This means that equal amounts of energy must be emitted in the form of waves, with frequencies ranging from 1 to 2 million waves per second, and in the form of waves with frequencies ranging from 2 to 3 million waves per second. And since there are infinitely many different frequencies, the total emitted energy must be infinite. To eliminate this obviously absurd conclusion, the German scientist Max Planck proposed in 1900 a hypothesis stating that light, X-rays, and other waves cannot be emitted with arbitrary intensity, but must be emitted only in certain portions, which Planck called quanta. Furthermore, Planck suggested that each quantum of radiation carries a specific amount of energy, which increases with the frequency of the waves. Thus, at sufficiently high frequencies, the energy of a single quantum can exceed the available energy, and therefore high-frequency radiation will be suppressed, making the rate at which the body loses energy finite. The quantum hypothesis aligned perfectly with the observed values of the intensity of radiation from hot bodies, but its implications for determinism were unclear. It was not until 1926 that another German scientist, Werner Heisenberg, formulated the famous uncertainty principle. To predict the position and velocity of a particle, one must be able to make an accurate measurement of its position and velocity at the present moment. Obviously, this requires directing light at the particle. Some of the light waves will scatter off it, allowing us to determine the particle's position in space. However, the accuracy of this measurement will be no better than the distance between the crests of two adjacent waves, and therefore, to accurately measure the position of a particle, a short pulse of light is necessary. According to Planck's hypothesis, light cannot be used in arbitrarily small portions, and there is no smaller portion than a single quantum. This quantum of light will disturb the motion of the particle and unpredictably alter its velocity. Moreover, the more accurately the position is measured, the shorter the light waves must be, and consequently, the greater the energy of a single quantum will be. This means that the disturbance in the particle's velocity will increase. In other words, the more precisely you try to measure the position of a particle, the less precise the measurements of its velocity will be, and vice versa. Heisenberg showed that the uncertainty in the position of a particle multiplied by the uncertainty in its velocity and its mass cannot be less than a certain number, which is now called Planck's constant. This number is independent of the method used to measure the position or velocity of the particle or the type of particle itself. Thus, Heisenberg's uncertainty principle is a fundamental and mandatory property of our world. The uncertainty principle has far-reaching implications for our perception of the surrounding world. Even after more than 50 years, many philosophers have not agreed with them, and these implications remain a subject of debate. The uncertainty principle marked the end of Laplace's dreams of a scientific theory that would provide a fully deterministic model of the universe. After all, how can one accurately predict the future if one cannot even make precise measurements of the current state of the universe? Of course, we can imagine that there exists a set of laws that completely determine events for some supernatural being capable of observing the current state of the universe without disturbing it. However, such models of the universe are of no interest to us, mere mortals. It is perhaps better to apply the principle of economy, known as Occam's razor, and eliminate all positions of the theory that cannot be observed. Adopting this approach, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac revised mechanics and arrived at a new theory, quantum mechanics, based on the uncertainty principle. In quantum mechanics, particles no longer possess such definite and independent characteristics as position in space and velocity, which are inaccessible to observation. Instead, they are characterized by a quantum state, which represents a combination of position and velocity. Quantum mechanics, in general, does not predict that an observation should yield a single definite result. Rather, it predicts a range of different results and provides the probability of each. This means that if we perform the same measurement on many identical systems with the same initial state, we would find that in some cases the measurement result equals A, in others it equals B, and so on. We can predict how many cases will yield results of A and B, but determining the result of each specific measurement is impossible. Thus, quantum mechanics introduces an inevitable element of unpredictability or randomness into science. Einstein was very vocal against this concept, despite the significant role he himself played in its development. For his immense contributions to quantum theory, Einstein was awarded the Nobel Prize, but he could never accept that the universe is governed by chance. All of Einstein's sentiments found expression in his famous saying, "God does not play dice." However, most other scientists were inclined to accept quantum mechanics because it aligned perfectly with experimental results. Quantum mechanics is indeed an outstanding theory and underpins nearly all modern science and technology. The principles of quantum mechanics form the basis for the operation of semiconductor and integrated circuits, which are crucial components of electronic devices such as televisions and computers. Modern chemistry and biology are built upon quantum mechanics. The only area of physics that has yet to properly utilize quantum mechanics is the theory of gravity and the theory of the large-scale structure of the universe. Despite the fact that light radiation consists of waves, according to Planck's hypothesis, light behaves in some sense as if it is made up of particles. Radiation and absorption of light occur only in portions or quanta. The uncertainty principle states that particles behave in some sense like waves. They do not have a definite position in space, but are spread out across it with a certain probability distribution. Quantum mechanical theory employs a completely new mathematical framework that no longer describes the real world based on concepts of particles and waves. These concepts can now only be related to the results of observations in this world. Thus, quantum mechanics introduces a partial wave-particle duality. In some cases, it is convenient to consider particles as waves, while in others, it is better to consider waves as particles. This leads to an important conclusion. We can observe so-called interference between two waves or particles. The crests of one wave may, for example, coincide with the troughs of another, causing the two waves to cancel each other out. They can also amplify each other by summing, as one might expect, resulting in higher waves. A well-known example of light interference is the iridescent soap bubbles reflecting different colors of the rainbow. This phenomenon occurs due to the reflection of light from two surfaces of a thin film of water that forms the bubble. White light contains all possible wavelengths corresponding to different colors. The crests of some waves reflected from one surface of the film coincide with the troughs of waves of the same wavelength reflected from the second surface of the bubble. Thus, the reflected light will lack colors corresponding to these wavelengths, resulting in colorful reflections. Therefore, due to the wave-particle duality that emerged in quantum mechanics, particles can also experience interference. A widely known example of such interference is the double-slit experiment. Consider a screen with two narrow parallel slits cut into it. On one side of the screen with the slits is a light source of a specific color, meaning a specific wavelength. The light mainly hits the surface of the screen, but a small portion passes through the slits. Next, imagine a screen for observation set up on the other side of the light source. Then, at any point on the observation screen, light waves from both slits will arrive, but the distance traveled by the light through the slits from the source to the screen will generally differ. This means that the waves passing through the slits will hit the screen in different phases. In some places, they will cancel each other out, while in others, they will reinforce each other. As a result, a characteristic pattern of dark and light stripes will appear on the screen. Remarkably, the same stripes occur when the light source is replaced with a source of particles, say electrons, emitted at a specific speed. This indicates that they correspond to waves of a specific wavelength. The described phenomenon is even stranger because when there is only one slit, no stripes appear, and the screen shows just a uniform distribution of electrons. One might assume that adding another slit would simply increase the number of electrons hitting each point on the screen. But in reality, due to interference, the number of these electrons decreases in some places. If electrons are passed through the slits one at a time, one might expect that each would pass through either one slit or the other, behaving as if the slit through which it passed was the only one. In that case, a uniform distribution should appear on the screen. However, stripes still appear even when electrons are emitted one by one. This means that each electron must pass through both slits simultaneously. The phenomenon of particle interference has been crucial for our understanding of the structure of atoms, the smallest bricks from which we and everything around us are made. At the beginning of the century, it was believed that atoms are similar to a solar system. Electrons, negatively charged particles, orbit around a positively charged nucleus at the center. It was assumed that electrons are held in their orbits by the attractive forces between positive and negative charges, similar to how gravitational attraction between the Sun and the planets keeps the planets in orbit. This explanation faced a significant difficulty. Before the advent of quantum mechanics, the laws of mechanics and electricity predicted that electrons should lose energy and spiral inward toward the nucleus. This would mean that atoms, and thus all matter, should rapidly collapse into a state of very high density. A partial solution to this problem was found in 1913 by the Danish scientist Niels Bohr. Bohr postulated that electrons can only move along specific orbits at certain distances from the central nucleus. If it were also assumed that only one or two electrons could occupy each of these orbits, then the problem of atomic collapse would be resolved, as electrons spiraling inward could only fill the orbits with minimal radii and energies. This model explained the structure of the simplest atom, the hydrogen atom, which has only one electron orbiting around its nucleus. However, it was unclear how to extend this approach to more complex atoms. Additionally, the assumption of a limited number of allowed orbits seemed quite arbitrary. This difficulty was resolved by the new theory, quantum mechanics. It turned out that an electron orbiting a nucleus can be represented as a wave, the length of which depends on its speed. Along certain orbits, a whole, rather than a fractional number of electron wavelengths fits. When moving along these orbits, the crests of the waves will align at each turn, causing the waves to reinforce one another. Such orbits correspond to Bohr's allowed orbits, along which an integer number of electron wavelengths fits. Each crest will eventually be compensated by a trough as the electron orbits. Such orbits will not be allowed. The American scientist Richard Feynman devised a beautiful method that allows for a visual representation of the wave-particle duality. Feynman introduced the concept of summing over paths. In this approach, unlike classical and quantum theory, there is no assumption that a particle must have a single trajectory in space-time. Instead, it is considered that a particle can move from A to B along any possible path. Each trajectory is associated with two numbers. One describes the amplitude of the wave, and the other indicates its position in the cycle, crest or trough. To determine the probabilities of transitioning from A to B, one must sum the waves for all these trajectories. If several neighboring trajectories are compared, their phases or positions in the cycle will vary greatly. This means that the waves corresponding to such trajectories will almost completely cancel each other out. However, for some average trajectories, the phases will change little as one moves from trajectory to trajectory, and the corresponding waves will not cancel each other out. Such trajectories correspond to Bohr's allowed orbits. Based on such representations, recorded in a specific mathematical form, it became possible to calculate the allowed orbits for more complex atoms, and even for molecules consisting of several atoms held together by electrons whose orbits encompass more than one nucleus. Since the structure of molecules and the reactions between them form the foundation of all chemistry and biology, quantum mechanics fundamentally allows us to predict everything we see around us, with the accuracy permitted by the uncertainty principle. However, in practice, calculations for systems containing many electrons are so complex that they are simply impossible to perform. The large-scale structure of the universe appears to adhere to Einstein's general theory of relativity. This theory is called classical because it does not take into account the quantum mechanical uncertainty principle, which must be considered to reconcile with other theories. We do not encounter contradictions with observational results because all gravitational fields we typically deal with are very weak. However, according to the aforementioned singularity theorem, gravitational fields must become very strong in at least two situations, in the case of black holes and in the case of the Big Bang. In such strong fields, quantum effects must be significant. Therefore, the classical general theory of relativity, which predicted points where density becomes infinite, in a sense brought about its own downfall, just as classical, non-quantum mechanics condemned itself to failure with the conclusion that atoms must collapse until their density becomes infinite. We do not yet have a complete theory in which the general theory of relativity is consistently unified with quantum mechanics, but we do know some properties of the future theory, including what follows from these properties concerning black holes and the Big Bang. We will discuss this in subsequent chapters, but for now, let us focus on the latest attempts to unify our understanding of all other forces of nature into a single quantum theory. Aristotle believed that matter in the universe consists of four fundamental elements: earth, air, fire, and water, acted upon by two forces: the force of gravity, which pulls earth and water down, and the force of lightness, which causes fire and air to rise. This approach to the structure of the universe, dividing everything into matter and forces, persists to this day. According to Aristotle, matter is continuous, meaning any piece of matter can be infinitely divided into smaller and smaller pieces without ever reaching a tiny grain that cannot be divided further. However, some other Greek philosophers, such as Democritus, held that matter inherently has a granular structure and that everything in the world consists of a large number of different atoms. The Greek word atom means indivisible. The debate continued without any real evidence to support either side. Finally, in 1803, the English chemist and physicist John Dalton demonstrated that the fact that chemical substances always combine in specific proportions can be explained by assuming that atoms group together into units called molecules. However, until the beginning of our century, the debate between the two schools had not been resolved in favor of the atomists. A significant contribution to resolving this debate was made by Einstein in his paper written in 1905, just weeks before his famous work on special relativity. Einstein pointed out that the phenomenon known as Brownian motion, the irregular chaotic movement of tiny particles suspended in water, can be explained by the impacts of the atoms of the liquid on these particles. By that time, there were already some grounds to consider that atoms might not be indivisible either. A few years earlier, J. Thomson from Trinity College in Cambridge discovered a new particle of matter, the electron, which has a mass less than 1,000th that of the lightest atom. Thomson's experimental setup resembled a modern television cathode ray tube. A hot, glowing metallic wire served as a source of electrons. Since electrons are negatively charged, they were accelerated in an electric field and moved toward a screen coated with a phosphorescent material. When the electrons struck the screen, flashes of light appeared. It soon became clear that these electrons must be emitted from atoms, and in 1911, the English physicist Ernest Rutherford finally proved that atoms of matter indeed have an internal structure. They consist of a tiny positively charged nucleus, with electrons rotating around it. Rutherford reached this conclusion by studying how alpha particles, positively charged particles emitted by radioactive substances, are deflected when they collide with atoms. Initially, it was thought that the nucleus of an atom consisted of electrons and positively charged particles, which were named protons from the Greek word protas, meaning primary, because protons were considered the fundamental building blocks of matter. However, in 1932, James Chadwick, a colleague of Rutherford at Cambridge University, discovered that there were other particles in the nucleus, neutrons, which have a mass nearly equal to that of protons, but are uncharged. For this discovery, he was awarded the Nobel Prize, and later became the head of the college at Cambridge University. However, he had to resign from this position due to disagreements with his colleagues. The college was constantly embroiled in fierce debates that began. After the war, when a group of returning youth voted against allowing the older staff to retain their positions, which they had held for many years. Even 20 years ago, protons and neutrons were considered elementary particles. But experiments involving the interaction of protons and electrons moving at high speeds showed that protons are actually made up of even smaller particles. Murray Gell-Mann, a theorist from the California Institute of Technology, named these particles quarks. In 1969, Gell-Mann was awarded the Nobel Prize for his research on quarks. The name quark was taken from a nonsensical line in James Joyce's poetry: 3 quarks for muster mark. Ideally, the word quark should be pronounced similarly to quart and court, where the letter T at the end is replaced by the letter K, but it is usually pronounced to rhyme with lark. Several varieties of quarks are known, and it is believed that there are at least 6 flavors: up quark, down quark, strange quark, charm quark, bottom quark, and top quark. Each flavor can also be one of 3 colors: red, green, and blue. It should be emphasized that these are merely designations, as the size of quarks is significantly smaller than the wavelength of visible light, and therefore they do not possess colors in the usual sense. The fact is that modern physicists enjoy inventing names for new particles without limiting their imagination to the Greek alphabet. Protons and neutrons are made up of 3 quarks of different colors. A proton contains 2 up quarks and 1 down quark, while a neutron contains 2 down quarks and 1 up quark. Particles can be constructed from other quarks: strange, charm, and bottom quarks, but all these quarks have much greater mass and decay very quickly into protons and neutrons. We already know that neither atoms nor the protons and neutrons within them are indivisible. Therefore, the question arises: what are the true elementary particles, the fundamental building blocks from which everything is made? Since the wavelengths of light are significantly larger than the sizes of atoms, we have no hope of seeing the constituent parts of an atom in the usual way. For this purpose, a significantly smaller wavelength is required, and we have learned that according to quantum mechanics, all particles are actually also waves, and the higher the energy of a particle, the shorter its corresponding wavelength. Thus, our answer to the posed question depends on how high the energy of the particles at our disposal is, as it determines how small the scale of the lengths we will be able to observe. The units in which particle energy is typically measured are called electron volts. Thomson used an electric field in his experiments to accelerate electrons. 1 electron volt is the energy gained by an electron in an electric field of 1 volt. In the 19th century, when only particles with energies of a few electron volts, released in chemical reactions like combustion, could be used, atoms were considered the smallest parts of matter. In Rutherford's experiments, the energies of alpha particles were in the millions of electron volts, and then we learned to accelerate particles using electromagnetic fields to energies in the millions and then in the billions of electron volts. Thus, we learned that the particles that were considered elementary 20 years ago are actually made up of smaller particles. What if, when moving to even higher energies, it turns out that these smaller particles, in turn, consist of even smaller ones? Of course, this is a plausible situation, but we currently have some theoretical grounds to believe that we already possess or are close to possessing knowledge about the fundamental building blocks from which everything in nature is constructed. Everything in the universe, including light and gravity, can be described based on the concept of particles, taking into account partial wave duality. Imagine particles as small spinning tops rotating around their axis. However, this picture can be misleading because in quantum mechanics, particles do not have a well-defined axis of rotation. In fact, the spin of a particle provides us with information about what that particle looks like when viewed from different angles. A particle with spin 0 resembles a point. It looks the same from all sides. A particle with spin 1 can be compared to an arrow. From different sides, it looks different and only appears the same after a complete rotation of 360 degrees. A particle with spin 2 can be compared to an arrow sharpened at both ends. Any of its positions repeats after a half turn of 180 degrees. Similarly, a particle with a higher spin returns to its original state after rotating through an even smaller portion of a full rotation. This is all quite obvious, but what is astonishing is that there are particles that do not return to their original appearance after a full rotation. They need to be rotated twice completely. Such particles are said to have a spin of 1/2. All known particles in the universe can be divided into 2 groups: particles with spin 1/2, which make up the matter in the universe, and particles with spin 0, 1, and 2, which, as we will see, create the forces acting between the particles of matter. Matter particles obey the so-called Pauli exclusion principle, discovered in 1925 by the Austrian physicist Wolfgang Pauli. In 1945, he was awarded the Nobel Prize for his discoveries. He was the perfect example of a theoretical physicist. It is said that his mere presence in a city disrupted the course of all experiments. The Pauli principle states that 2 identical particles cannot exist in the same state, meaning they cannot have the same coordinates and velocities with the precision defined by the uncertainty principle. The Pauli principle is extremely important because it allowed for the explanation of why, Under the influence of forces created by particles with spin 0, 1, and 2, matter particles do not collapse into a state of very high density. If matter particles have very close coordinate values, their velocities must be different, and therefore they cannot remain in points with those coordinates for long. If the Pauli principle had not been involved in the creation of the world, quarks would not have been able to combine into distinct, well-defined particles, protons and neutrons, which in turn would not have been able to combine with electrons to form distinct, well-defined atoms. Without the Pauli principle, all these particles would have scattered and turned into a more or less homogeneous dense jelly. A correct understanding of the electron and other particles with spin 1/2 did not exist until 1928, when Paul Dirac proposed a theory to describe these particles. Subsequently, Dirac obtained a mathematics chair at Cambridge, which had once been held by Newton. Dirac's theory was the first of its kind to reconcile quantum mechanics and special relativity. It provided a mathematical explanation of why the spin of the electron is 1/2, meaning why, after a single complete rotation, the electron does not return to its original appearance, but does so after a double rotation. Dirac's theory also predicted that the electron should have a partner, an anti-electron, or positron. The discovery of the positron in 1932 confirmed Dirac's theory, and in 1933 he received the Nobel Prize in Physics. We now know that every particle has a corresponding antiparticle with which it can annihilate. In the case of particles that mediate interactions, a particle and its antiparticle could exist as whole anti-words and anti-people made up of antiparticles. But if you encounter an anti-me, do not attempt to shake hands with it. A blinding flash of light will occur, and you will both disappear. The question of why there are far more particles around us than antiparticles is extremely important. In quantum mechanics, it is assumed that all forces or interactions between matter particles are mediated by particles with integer spins equal to 0, 1, or 2. A matter particle, such as an electron or a quark, emits a particle that serves as the mediator of the interaction, and as a result of recoil, it changes the speed of the matter particle. The mediator particle then collides with another matter particle and is absorbed by it. This collision changes the speed of the second particle as if a force were acting between these two matter particles. The mediator particles of interactions have one important property. They do not obey the Pauli exclusion principle. This means there are no restrictions on the number of exchanged particles, so the resulting interaction force can be very large. However, if the mass of the mediator particles is large, their creation and exchange will be hindered over long distances. Thus, the forces they carry will be short range. If the mediator particles do not possess mass, long-range forces will arise. The mediator particles exchanged between matter particles are called virtual because, unlike real particles, they cannot be directly registered using a particle detector. However, we know that virtual particles exist because they create measurable effects. It is through virtual particles that forces arise between matter particles. Under certain conditions, particles with spins 0, 1, and 2 can also exist as real particles, in which case they can be directly registered. From the perspective of classical physics, such particles appear to us as waves, such as light or gravitational waves. They are sometimes emitted during interactions of matter particles, which occur through the exchange of mediator particles, For example, the electric force of repulsion between two electrons arises through the exchange of virtual photons, which cannot be directly registered. But if electrons fly past each other, real photons may be emitted, which can be detected as light waves. Mediator particles can be divided into 4 types, depending on the magnitude of the interaction they carry and the particles they interact with. It should be emphasized that this division is entirely artificial. This scheme is convenient for developing specific theories, but nothing more serious is implied. Most physicists hope that eventually a unified theory will be created in which all 4 forces would turn out to be varieties of the same force. Many even see this as the main goal of modern physics. Recently, attempts to unify the 3 forces have been successful. We will discuss the status of including gravity in such a unification a bit later. So, the first type of force is the gravitational force. Gravitational forces are universal. This means that every particle is subject to the gravitational force, the magnitude of which depends on the mass or energy of the particle. Gravity is much weaker than each of the other 3 forces. It is a very weak force that we would not notice at all if it were not for 2 specific properties. The gravitational force acts over long distances and is always an attractive force. Consequently, very weak gravitational forces between individual particles in 2 large bodies, such as the Earth and the Sun, can sum up to create a very large force. The other 3 types of interactions either act only over short distances or are sometimes repulsive and sometimes attractive, which generally leads to compensation. In the quantum mechanical approach to the gravitational field, it is believed that the gravitational force acting between 2 matter particles is mediated by a particle with spin 2, called the graviton. The graviton has no mass, and therefore the force it carries is long range. The gravitational interaction between the Sun and the Earth is explained by the exchange of gravitons between the particles that make up the Earth and the Sun. Although only virtual particles are involved in the exchange, the effect they create is undoubtedly measurable, as this effect is the Earth's rotation around the Sun. Real gravitons propagate as waves, which in classical physics are called gravitational waves, but they are very weak, and they are so difficult to detect that no one has succeeded in doing so yet. The next type of interaction is created by electromagnetic forces, which act between electrically charged particles, such as electrons and quarks, but do not account for the interaction of uncharged particles like gravitons. Electromagnetic interaction is much stronger than gravitational interaction. The electromagnetic forces acting between 2 electrons are approximately 1,000,000,000,000,000,000,000,000 times greater than the gravitational force. However, there are 2 types of electric charge, positive and negative. Between 2 positive charges, as well as between 2 negative charges, there is a repulsive force, while between a positive and a negative charge, there is an attractive force. In large bodies, such as the Earth or the Sun, the content of positive and negative charges is nearly equal, and therefore the attractive and repulsive forces nearly cancel each other out, leaving very little net electromagnetic force. However, on small scales, such as atoms and molecules, electromagnetic forces dominate. Under the influence of electromagnetic attraction between negatively charged electrons and positively charged protons in the nucleus, electrons in an atom revolve around the nucleus, just as the Earth revolves around the Sun, due to gravitational attraction. Electromagnetic attraction is described as a result of the exchange of a large number of massless particles with spin 1 called photons. As with gravitons, the photons that mediate the exchange are virtual. But when an electron transitions from one allowed orbit to another, closer to the nucleus, energy is released, resulting in the emission of a real photon, which can be observed by the human eye as visible light, or with the help of some photon detector, such as photographic film. Similarly, when a real photon collides with an atom, an electron may transition from one orbit to another, farther from the nucleus. This transition occurs due to the energy of the photon, which is absorbed by the atom. The third type of interaction is called weak interaction. It is responsible for radioactivity and exists between all matter particles with spin 1/2, but does not involve particles with spin 0, 1, and 2, photons and gravitons. Until 1967, the properties of weak forces were poorly understood, but in that year, Abdus Salam, a theorist from Imperial College London, and Steven Weinberg from Harvard University simultaneously proposed a theory that unified weak interaction with electromagnetic interaction, similar to how Maxwell unified electricity and magnetism 100 years earlier. Weinberg and Salam hypothesized that in addition to photons, there are 3 other particles with spin 1, collectively called the heavy vector bosons, which are the mediators of weak interaction. These bosons were designated by the symbols W+, W-, and Z0. The mass of each of them is 100 giga-electron volts. A giga-electron volt means 1,000 million electron volts. The Weinberg-Salam theory possesses the property of so-called spontaneous symmetry breaking. This means that particles are completely different at low energies, but at high energies, they are actually the same particle in different states. This is somewhat analogous to the behavior of a ball in a game of roulette. At all high energies, that is, when the wheel is spinning quickly, the ball behaves almost the same. It spins continuously. But when the wheel slows down, the energy of the ball decreases, and eventually it falls into one of the 37 pockets on the wheel. In other words, at low energies, the ball can exist in 37 states. If we could somehow observe the ball only at low energies, we would think that there are 37 different types of balls. The Weinberg-Salam theory predicted that at energies significantly exceeding 100 giga-electron volts, the 3 new particles and the photon should behave identically, while at lower energies, the particles should behave as they usually do in most situations. This symmetry should be broken. The masses of the W+, W-, and Z0 bosons were predicted to be large so that the force they create would have a very short range. When Weinberg and Salam proposed their theory, few believed them. At the powerful accelerators of that time, it was impossible to reach the energy of 100 giga-electron volts necessary to create real W+, W-, and Z0 particles. However, about 10 years later, the predictions made by this theory at low energies were so well confirmed experimentally that Weinberg and Salam were awarded the Nobel Prize in 1979, jointly with Sheldon Glashow, also from Harvard, who proposed a similar unified theory of electromagnetic and weak nuclear interactions. The Nobel Prize Committee was spared the trouble that might have arisen had it turned out that it made a mistake when it discovered 3 massive partners of the photon with the correct mass values and other predicted characteristics at CERN in 1983. Carl Rubia, who led a group of several hundred physicists responsible for this discovery, received the Nobel Prize in 1984, awarded to him jointly with CERN engineer Simon van der Meer, the author of the antiproton accumulator project used in the experiment. In our time, it is extremely difficult to leave a mark in experimental physics unless you are already at the top. The strong nuclear interaction represents the fourth type of interaction that holds quarks inside protons and neutrons inside atomic nuclei. The mediator of strong interaction is another particle with spin 1, called the gluon. Gluons interact only with quarks and other gluons. The strong interaction has one extraordinary property. It possesses containment. The essence is that particles are always held in colorless combinations. A single quark cannot exist on its own because it would then have to have color: red, green, or blue. Therefore, a red quark must be connected with a green and a blue one through gluons. Red plus green plus blue equals white. Such a triplet turns out to be a proton or a neutron. There is another possibility where a quark and an antiquark combine into a pair: red plus anti-red, or green plus anti-green, or blue plus anti-blue equals white. Such combinations make up particles called mesons. These particles are unstable because a quark and an antiquark can annihilate each other, producing electrons and other particles. Similarly, a single gluon cannot exist on its own due to confinement because gluons also possess color. Consequently, baryons must group in such a way that their colors sum to white. The described group of gluons forms an unstable particle called a gluon ball. We cannot observe a separate quark or gluon. And does the law of confinement imply that the very concept of quarks and gluons is somewhat metaphysical? No, because the strong interaction is characterized by another property called asymptotic freedom. Thanks to this property, the concepts of quarks and gluons become quite definite. At ordinary energies, the strong interaction is indeed strong and tightly binds quarks together. But, as experiments at powerful accelerators show, at high energies, the strong interaction noticeably weakens, and quarks and gluons begin to behave almost like free particles. As a result of the successful unification of electromagnetic and weak interactions, attempts have been made to connect these two types of interactions with strong interaction to produce what is known as grand unification theory. This name is somewhat exaggerated. First, grand unification theories are not that grand. And second, they do not completely unify all interactions because they do not include gravity. Moreover, all these theories are actually incomplete because they contain parameters that cannot be predicted theoretically and must be calculated by comparing theoretical and experimental results. Nevertheless, such theories can be a step toward a complete unification encompassing all interactions. The main idea behind constructing grand unification theory is as follows. As already mentioned, strong interaction becomes weaker at high energies than at low. At the same time, electromagnetic and weak forces are asymptotically free, and at high energies, they grow. Then, at some very high energy value, at the energy of grand unification, these three forces could equalize and become simply varieties of the same force. Grand unification theories predict that at this energy, different matter particles with spin 1/2, such as quarks and electrons, would also cease to differ, which would be another step toward unification. The value of the grand unification energy is not very well known, but it should be at least 1,000 million giga-electron volts. In modern generation accelerators, particles collide with energies around 100 giga-electron volts, and in future projects, this value is expected to increase to several thousand giga-electron volts. However, to accelerate particles to the energy of grand unification, an accelerator the size of the solar system would be needed. It is unlikely that anyone would dare to finance this in the current economic situation. This is why direct experimental verification of grand unification theory is impossible. But here, as in the case of the electroweak unified theory, there are low-energy consequences that can be tested. The most interesting of such consequences is that protons, which make up a large part of the mass of ordinary matter, may spontaneously decay into lighter particles, such as anti-electrons. The reason is that at the energy of grand unification, there is no significant difference between quarks and anti-electrons. The three quarks inside a proton usually do not possess enough energy to transform into an anti-electron, but one of the quarks may randomly gain sufficient energy for this transformation. Because, due to the uncertainty principle, it is impossible to precisely fix the energy of quarks within a proton, the proton must decay. However, the probability that a quark will have sufficient energy is so low that one would have to wait at least 1 million years with 30 zeros, which is much longer than the time that has elapsed since the Big Bang, which does not exceed 10 billion years or so, a 1 with 10 zeros. Hence, it follows that the possibility of spontaneous proton decay cannot be experimentally verified. However, it is possible to increase the probability of observing proton decay by studying a very large number of protons. For example, observing 1 with 31 zeros protons over the course of a year. It is hoped that, according to one of the simplest grand unification theories, more than one proton decay will be detected. Several such experiments have already been conducted, but they have not provided definitive information about proton or neutron decays. One of the experiments, which used 8,000 tons of water, was conducted in a salt mine in Ohio, and to exclude cosmic interference that could be mistaken for proton decay, since no proton decay was registered throughout the experiment, it can be calculated that the lifetime of a proton must be greater than 10 million years with 31 zeros. This result exceeds the prediction of the simplest grand unification theory, but there are also more complex theories that provide a higher estimate. Testing them will require even more precise experiments with even larger amounts of matter. Despite the difficulties in observing proton decay, it is not excluded that our very existence is a consequence of the reverse process, the formation of protons, or more simply, quarks, at the very initial stage when there were no more quarks than antiquarks. Such a picture of the early universe seems the most natural. Earthly matter mainly consists of protons and neutrons, which in turn are made up of quarks, but it contains neither antiprotons nor antineutrons made of antiquarks, except for the few that have been produced at large accelerators. Experiments with cosmic rays confirm that the same is true for all matter in our galaxy. It contains neither antiprotons nor antineutrons, except for the small number of antiparticles that arise from the birth of particle-antiparticle pairs during high-energy collisions. If there were large regions of antimatter in our galaxy, one would expect strong radiation at the boundaries between matter and antimatter, where numerous collisions of particles and antiparticles would occur, annihilating each other and emitting high-energy radiation. We have no direct indications of whether the matter of other galaxies consists of protons and neutrons, or of antiprotons and antineutrons, but it must consist of particles of one type. Within a single galaxy, there cannot be a mixture of particles and antiparticles, as their annihilation would produce powerful radiation. Therefore, we believe that all galaxies consist of quarks, not antiquarks. It is unlikely that some galaxies consist of matter while others consist of antimatter. But why should there be so many more quarks than antiquarks? Why is their number not equal? We are very fortunate that this is the case, because if quarks and antiquarks were equal in number, almost all quarks and antiquarks would have annihilated each other in the early universe, filling it with radiation but leaving little matter. No galaxies, no stars, no planets on which human life could develop. With the help of grand unification theory, it is possible to explain why there should now be more quarks in the universe than antiquarks, even if they were equal in number at the very beginning. As we already know, in grand unification theories at high energies, quarks can transform into anti-electrons, and reverse processes are possible, where antiquarks transform into electrons, and electrons and anti-electrons into antiquarks and quarks. Once, at a very early stage of the universe's development, it was so hot that the energies of the particles were sufficient for such transformations. But why did quarks end up being more numerous than antiquarks? The reason lies in the fact that the laws of physics are not quite the same for particles and antiparticles. It has been considered that the laws of physics are invariant under three symmetry transformations: C, P, and T. Symmetry. C means that all laws are the same for particles and antiparticles. Symmetry P means that the laws of physics are the same for any phenomenon and its mirror image. The mirror image of a particle rotating clockwise would be a particle rotating counterclockwise. Finally, the meaning of symmetry T is that if the direction of motion of all particles and antiparticles is reversed, the system will return to the state it was in before. In other words, the laws are the same when moving forward or backward in time. In 1956, two American physicists, Charles Cowan and Jennings Young, suggested that weak interaction is not actually invariant under P transformations. In other words, as a result of weak interaction, the evolution of the universe may proceed differently than the evolution of its mirror image. In the same year, Qianxiong Wu, a colleague of Li and Yang, managed to prove that their hypothesis was correct. By aligning the magnetic field of the nuclei of radioactive atoms so that their spins were directed the same way, she showed that more electrons are emitted in one direction than in another. Next year, Li and Yang were awarded the Nobel Prize for their discovery. It turned out that weak interaction does not obey C symmetry. This means that a universe composed of antiparticles would behave differently than our universe. It became clear that weak interaction must still adhere to the combined CPT symmetry, meaning that the development of the universe should occur in the same way as the development of its mirror image, if it were reflected in a mirror and each particle replaced with its antiparticle. However, in 1964, two more Americans, James Cronin and Val Fitch, discovered that the decay of particles known as K-mesons even violates the symmetry of special relativity. As a result, in 1980, Cronin and Fitch received the Nobel Prize for their work. What a tremendous number of prizes have been awarded for works demonstrating that the universe is not as simple as it seems. There exists a mathematical theorem stating that any theory adhering to quantum mechanics and relativity must always be invariant under the combined symmetry of special and general relativity. In other words, the universe will not change if particles and antiparticles are replaced. Everything is reflected in a mirror, and the direction of time is also reversed. But Cronin and Fitch showed that if particles and antiparticles are replaced and a mirror reflection is made without reversing the direction of time, the universe behaves differently. Therefore, when time is reversed, the laws of physics must change, meaning they are not invariant under symmetry. It is clear that in the early universe, symmetry was violated when time flows forward. The universe expands, and if time were to flow backward, the universe would begin to contract. Since there are forces that are not invariant under symmetry, it follows that as the universe expands under the influence of these forces, positrons must transform into quarks more often than electrons into antiquarks. Then, as the universe expanded and cooled, antiquarks and quarks should have annihilated. But since there would be more quarks than antiquarks, quarks would remain in slight excess, and these are the very quarks that make up the matter we see today, and from which we ourselves are formed. Thus, our very existence can be viewed as a confirmation of the grand unification theory, albeit only as a qualitative confirmation. Uncertainties arise because we cannot predict how many quarks will remain after annihilation, nor do we even know if the remaining particles will be quarks or antiquarks. However, if you were excessively left with antiquarks, you could simply rename them as quarks and quarks as antiquarks. The grand unification theory does not include gravitational interaction, which is not particularly significant, because gravitational forces are so small that their influence can be neglected when dealing with elementary particles or atoms. However, the fact that gravitational forces are long-range and always attractive means that the results of their effects always add up. Therefore, if there is a sufficient quantity of matter particles, gravitational forces can become greater than all other forces. This is why the evolution of the universe is determined precisely by gravity. Even in the case of objects the size of stars, gravitational attraction can outweigh all other forces and lead to the collapse of a star. I have been researching black holes that can arise from such stellar collapse and the strong gravitational fields surrounding them. It was during this work that I first began to suspect how quantum mechanics and general relativity might influence each other. The initial glimpses of forms of this quantum theory of gravity still need to be developed.